So we make the molecular ion by smashing an electron into it. And when the electron smashes into that molecular ion, it puts kinetic energy into the molecule in addition to pushing the electron out. That kinetic energy starts to cause vibrations and stuff, and pieces will break off. Okay? And in fact, one of the things we can do is we can adjust the speed of those electrons that we're shooting. And if we turn the speed down, we reduce the amount of fragmentation. Okay? We're not going to worry about that. What I want to show you is some of the common fragments. Okay, so sorry, I messed up. Let me try again here. So imagine that we made this. This would be like a butyl radical cation, okay? What could happen is the carbon chain could break, okay? And so I'm going to show you a couple of examples of these. And when the carbon chain breaks, what happens is it breaks into a free radical on one side, which has no charge and we will not see, and a cation on the other side. So I'm going to start here with, let's break just at the methyl, okay? So the most likely result of this is going to be that. So we get a methyl radical on one side, and we get the propyl cation, and the mass of the propyl cation is approximately 12, 24, 36, 39, 41, 43. So we get an ion of mass 43. Okay? Now, it could also do this. In which case we would get a fragment, an ion of 15. This is more rare. And the reason for this is that the methyl cation, as we talked about, is pretty unstable. So this primary cation would be more stable. And so sort of the rules about cation stability do apply here, okay? So this is number one. This is number one rare. So then what we could do is we could do number two, and there's only going to be one of these because of the symmetry. But in theory, if we break at bond 2, this, what is this? This is 29. We'd have a peak at 29. Okay. And so what we would then do is we would look at our mass spectrum and we would look for peaks in this region. And this would tell us that we have a methyl group that can break off. We have an ethyl group that can break off, that kind of thing. One thing I want to point out is that, for example, this is M, which is the total molecule, minus 15. Okay, this is M minus 29, and so forth. And you can take any molecule, you can start breaking it. Okay. The one thing to notice is that if we look at, let's look at this one. Something like that. This has lots of modes to break, but probably the most common one that we would expect, no, not CH, my bad. Would be this, right? Because T-butyl is very stable. So what we would see in the mass spec is we would see a really large peak for the T-butyl. It'd be the largest peak. And then there would be other smaller peaks, but they would be much smaller than that T-butyl. Okay? And they can break again, so you can kind of keep going. All right, so that's one. Now, the next thing I want to talk to you about in fragmentation is resonance stabilized ions. Okay? So I'm going to start with a real simple one, and then I'm going to show you another really common one. So if we had this, sorry, that's not supposed to be plus minus, it's supposed to be plus dot. Come on. If we had this, we would basically expect this thing to fragment right here. And we already know the methyl cation is really unlikely, so probably the left-hand side is going to become a cation. And this is what we call an allylic cation. And it's stabilized by resonance. And so we would expect to see that thing to be a huge peak, right? And again, that has a mass of, what is that? 40, is that 41? Let me check. I don't have them memorized. They're 36, 38, 40, 41. So we would see a huge 41 peak in our mass spec. One of the really common ones that we see is if we have a phenyl ring, so for example, this is just an example, but there's lots of molecules that have phenyl rings in them. We expect to break right there, okay? So this carbon is called the benzylic carbon. It's the carbon that is adjacent to the phenyl ring, but not in the phenyl ring. And we're going to want to get a benzyl fragment. So what's going to happen is we're going to go all the way around along the chain. We're going to find this bond right next to the benzylic carbon. We'll break that. So that is going to give us that cation plus that radical, okay? And in this case, because the ethyl radical sort of, okay, we could also get the ethyl radical, I'm sorry, the ethyl cation and the benzylic radical, okay? But if we look at the mass of this thing, oh God, it's 91, I think. It's 72, 84, 85, 86, 87, 88, 89, 99. Yeah, it's 91. I haven't really done hardcore mass spec in a long time. I forget all my baseline numbers, but it's 91. So we would see a 91 peak. We would also probably expect to see also M minus 91 at some point. Okay, so that's aromatic fragments. Let me see here, and then finally, and this will be the end of the lecture. Sometimes we fragment and we lose a small molecule. Okay, really common one is water. So let me show you an example. I keep writing plus minus. So let's say we do this. Let me fix this. So this is essentially like an elimination reaction. We're going to take this off plus that. And it doesn't occur at the same step. It's like something grabs the hydrogen and then it pops the water off or whatever. But what we get then is we get this fragment. And then we get a molecule of water out, and water is super stable. So that's like a really strong driving force. And then this fragment, you can see, would have 36, 39, 40, 41, 42. This would be a 42, right? And so alcohols, especially, that's what this is, alcohol, tend to fragment. And if you look, this is going to be 18, right? So what we expect to see is M minus 18 as a really common fragment for that. We see a similar thing with carboxylic acids losing the CO2. And so that's another common thing.